Hello all, let's start with the second video of semiconductors. So in this case, I would be discussing more of MCQs to have better understanding what you will get in competitive exams and class 12 both. So let's start with it. So question number 15 says, which impurity is doped in silicon to form N-type semiconductor? Is it aluminium? Is it boron? Is it arsenic? Or it will none of these? So the right option in this case is arsenic, AS. Now moving on to the next question, it says in a semiconductor there are no free electrons at any temperature. The number of free electrons is more than that in a conductor. There is no free electrons at 0 Kelvin or none of these. So the right option in this case is that there are no free electrons at 0 Kelvin. That's the most appropriate one. Now the next one, the process of adding impurities to the semiconductor is called doping, none of. So the process of adding impurities is known as doping. Let's move on to question number 54. It says at room temperature a p-type semiconductor has large number of holes and few electrons. Yeah, that's right. In the case of 54th, A is the right answer because they asked for p-type semiconductor, like what is the characteristic of p-type. So it is always that number of holes is greater than number of electrons. Now moving on to next question. It says intrinsic semiconductor is electrically neutral. Extrinsic semiconductor have large number of current carriers, would be positively charged, negatively charged, or negatively charged depending upon the type of impurity that has been added. So in this case it will be D, that is electrically neutral. They are always electrically neutral, the extrinsic semiconductors. P-type semiconductors are made by adding impurity elements. Is it arsenic, is it phosphorus, is it boron, or is it bitumen? So in this it is part C, that is boron. A pure semiconductor behaves slightly as a conductor at room temperature, low temperature, high temperature, or D, B and C. So the right option in this case is A part, that is at room temperature. They behave slightly as a conductor on room temperature. If Np and Ne be the number of holes and conduction electrons in an extrinsic semiconductor, then it could be the part D because it depends on the nature of impurity, whether it is trivalent or pentavalent. That depends on that how they will be. In the case of N-type, we have more number of electrons as compared to holes, and in the case of P-type, we have more number of holes as compared to electrons. Let's move on to question number 59. Which of the following when added as an impurity into the silicon produces N-type semiconductor? So this has been repeated, and in this case we can mark it as phosphorus P. Then 60th, in P-type semiconductor the majority and minority charge carriers are respectively in P-type we have more number of holes. That means holes are the majority and minority in this case is electrons. So right option in this case is D. Let's move on to 61. So 61 in this case is if Ne and Vd be the number of electrons in drift velocity in a semiconductor when the temperature is increased. So when temperature is increased, out of these all, Ne increases and Vd decreases. Ne decreases and Vd increases. Both Ne and Vd increases. Both Ne and Vd decreases. So when the temperature is increased, the number of electrons increases and the drift velocity decreases. The right option for this will be A. Question number 62. When n-type of semiconductor is heated, number of electrons increases while that of hole decreases, or they remain same, or number of electrons and holes increases equally. So that's right, that number of electrons and holes increases equally as you increase the temperature of n-type semiconductor. Semiconductor is damaged by the strong current due to lack of free electrons, excess of electrons, excess of proton, none of these. So the right option in this case is that they possess excess of electrons. Charge density for intrinsic semiconductor is, intrinsic basically means that it is a pure type semiconductor. So in this case, it has a range of 10 raised to power 16. So the right option in this case is B part. Gallium arsenic is element semiconductor, alloy semiconductor, bad conductor, metallic semiconductor. The gallium arsenic is actually a alloy semiconductor because it is made up of two different elements, that is gallium and arsenic. Now moving on to 66. At ordinary temperature, an increase in temperature increases the conductivity of conductor, insulator, semiconductor or alloy. So the right option in this case is semiconductor. It can increase the conductivity. An N-type and P-type silicon can be obtained by doping pure silicon with. We need to obtain N-type and P-type. So we have here three options: arsenic and phosphorus, indium and aluminium, phosphorus and indium. So the right option in this case is phosphorus and indium respectively. Phosphorus for N-type and for P-type it could be indium. N-type semiconductors will be obtained when germanium is doped with phosphorus, aluminium, arsenic, both A or C. In this case, you know that phosphorus is there as done in the last question. So the right option is actually we can dope arsenic as well as phosphorus. So the right option is D in this case to get N-type. Next, moving on to the next one. The state of the energy gained by valence electron when the temperature is raised or when electric field is applied is called valence band, conduction band, forbidden band, none of these. So in this case it is conduction band. Moving on to next, it is 70th. So in this case it says at 0 Kelvin intrinsic semiconductors behave as a perfect conductor, a superconductor, a semiconductor or a perfect insulator. So the right option in this case is a perfect insulator. The intrinsic semiconductor, when kept at 0 Kelvin, it behaves as an insulator. So that's important. So let's start with question number 71. To obtain electrons as majority charge carriers in a semiconductor, the impurity mixed is monovalent, divalent, trivalent or pentavalent. So as it says electrons as majority charge carriers, that means it is a N-type. And if it is an N-type, that is under pentavalent impurity always. So it is pentavalent, the D part. Let's move on to next. So the next one is for germanium crystal, the forbidden energy gap in joules is. So it is actually the value for this is 1.12 into 10 raised to power minus 19. So this is the value of forbidden energy gap in joules. Let's move on to next one. In the terminology related to semiconductor, what is a hole? So in terminology with respect to semiconductor, what we consider hole as. So it is nothing but a space which was previously occupied by an electron. That's the appropriate answer for hole. Let's move on to next. In the 74th, if Ne and Nh are the number of electrons and holes in a semiconductor heavily doped with phosphorus, that means we have four options, that is Ne is equal to Nh, Ne is greater than NH, Ne is lesser than NH, and Ne is equal to and lesser than NH. So the right option from this is Ne is greater than NH. Why? Because it is a type of N-type. When phosphorus is added to a semiconductor, it forms a N-type. Let's move on to next one, 75th. In that it says in extrinsic semiconductor, the conduction band and valence band overlap. That's not true. The gap between conduction band and valence band is more than 16 electrovolt. Again, that's not true. The gap between conduction band and valence band is near about 1 electrovolt. And that's right. It's about 1 electrovolt in the case of extrinsic semiconductors. Let's move on to next. Resistivity of a semiconductor depends on shape of semiconductor, length of semiconductor, atomic nature of semiconductor, shape and atomic nature of semiconductor. So the right option in this case is atomic nature of semiconductor. It always depends on atomic nature, how the atomic nature is of semiconductor. Let's move on to next. Electronic configuration of germanium is 2, 8, 18 and 4. To make it extrinsic semiconductor, small quantity of antimony is added. So will it be a N-type or will it be a P-type germanium? So as antimony has been added, that means it will be a N-type germanium which has more number of electrons than holes at room temperature. Let's move on to next. It says at 0 degree Kelvin, a piece of germanium is. It becomes semiconductor, becomes good conductor, becomes bad conductor, has maximum conductivity. So in this case it is actually an insulator. So that means it is the C part, that is becomes bad conductor. Let's move on to next. In P-type semiconductor, germanium is grouped with boron, gallium, aluminium, all of these. So this is actually all of these. In N-type, majority charge carriers are electrons. P-type semiconductor is formed when as impurities mixed with silicon, aluminium impurities mixed with silicon, B impurities mixed in germanium, P impurities mixed in germanium. So option A or C or A or D or B or C or B and D. So in this case we have P-type semiconductor. So in this case it will be B is there. When aluminium is added to silicon, C is there. That means the right option for this is B and C. Let's move on to next, question number 82. In case of a semiconductor, which of the following statement is wrong? Doping increases conductivity, temperature coefficient of resistance is negative. Resistivity is in between that of a conductor and insulator. At absolute zero temperature, it behaves like a conductor. So the right option for 82 is at absolute zero temperature, it behaves actually like an insulator. So that means the wrong equation is the fourth one, D part. A N-type semiconductor is negatively charged, positively charged, neutral, or none of these. So it is all, remember that N-type, whether it is N-type or P-type, it is always a neutral and they have neutral charges. Let's move on to 84. When a potential difference is applied across the current passing through a semiconductor at 0 Kelvin is 0, at metal at 0 Kelvin is finite, if p-n diode at 300 Kelvin is finite, if it is reverse biased, all of these. So right option in this case will be all of the above. That means semiconductor at 0 K is 0, a metal at 0 Kelvin is finite, a p-n diode at 300 Kelvin is finite if it is reverse biased. That's all of the options are correct here. 85th. The value indicated by Fermi energy level in an intrinsic semiconductor is the average energy of electrons and holes, the energy of electrons in conduction band, the energy of holes in valence band, the energy of orbital region. So the value indicated by Fermi energy level for pure conductors is actually the average energy of electrons, energy possessed by electrons and holes. Let's move on to next. The dominant mechanism for motion of charge carriers in forward and reverse biased silicon p-n junction are drift in forward bias, diffusion in reverse bias, diffusion in forward bias, drift in reverse bias, diffusion in both forward and reverse bias, drift in both forward and reverse bias. So the right option in this case is B part, diffusion in forward bias and drift in reverse bias. 87. To obtain a p-type germanium semiconductor, it must be doped with. So A7th is actually indium. If you want to dope germanium, if you dope germanium with indium, it forms a p-type semiconductor. Question 88. So in this case it says in a pure semiconductor the current density is given by. So current density is actually given by J. In that they are dependent on N, Q and Vn and Vp. So according to for the pure semiconductor the equation is B part. Let's start with 89th. Silicon is a semiconductor. If a small amount of arsenic is added to it, then its electrical conductivity decreases, increases, remains unchanged, becomes zero. So the right option in this case is it increases. Whenever we dope anything to a pure semiconductor, the electrical conductivity increases. Let's move on to next. Electric current is due to drift of electrons in metallic conductors, semiconductors, both A and B, or none of these. So in this the right option is both A and B. It could be in metallic conductors or if in semiconductors. Let's move to 91. Fermi level of energy of an intrinsic semiconductor lies. Where does the Fermi level of intrinsic pure semiconductor lies? So the right option in this is in the middle of the forbidden gap. It is between the forbidden gap. In a semiconductor, the separation between conduction band and valence band is of the order of 100 electrovolt, 110 volt electrovolt, 1 electrovolt, 0 electrovolt. So in this case, the separation between semiconductors is about 1 electrovolt. Let Np and Ne be the number of holes and conduction electrons respectively in a semiconductor. Then the first one is incorrect. Np is equal to Ne. Again, second one is incorrect. Np is equal to Ne in an intrinsic semiconductor. Yeah, that's right. So C part is the right option. Let's move on to the 94th. An intrinsic semiconductor has 10 raised to power 18 meter raised to power minus 3 free electrons and is doped with pentavalent impurity atoms of density this. The free electron density will increase by dash orders of magnitude. So the right option is D, because as you can see it is 10 raised to power 18 in the case of intrinsic, and when they dope the pentavalent impurity it has been increased to 10 raised to power 24. So the order of magnitude has been increased by 6. Let's move on to 95th. The probability of electrons to be found in the conduction band of an intrinsic semiconductor at a finite temperature. So the right option in this case is only first, because it decreases exponentially with increasing band gap energy. Let's move on to 96. Doping of a semiconductor generally changes the resistivity as follows. It decreases, does not alter, may increase or decrease depending on the dopant, or increases. So resistivity is actually changes changes the resistivity as follows. It actually decreases the resistivity on doping of a semiconductor. Three semiconductors are arranged in the increasing order of their energy gap as follows. The correct arrangement is tellurium, germanium, silicon, tellurium, silicon, germanium, silicon, germanium, tellurium, silicon, tellurium, germanium. Right option in this case is A only because the correct arrangement is tellurium, germanium, then silicon. Let's move on to question number 98. It says, in insulators, the valence band is partially filled with electrons, the conduction band is partially filled with electrons, the conduction band is filled with electrons and valence band is empty. The conduction band is empty and valence band is filled with electrons. In the case of insulators, the valence band is filled with electrons and the conduction band is empty. So according to me or according to question, the right option is D part. 99. The energy gap of silicon is 1.14 electrovolt. The maximum wavelength at which silicon will begin absorbing energy is. So if you need to find if you need to find maximum wavelength, so the formula is lambda hc over Eg, and Eg is given in this case, H and C has a constant value. So put all those values and you will get your answer as 10,888 ampere. Let's look at the last one. The typical ionization energy of a donor in silicon is 10, 1, 0.1 or 0.001. So right option in this case is 1 electrovolt. That's all about today. I will continue with the next session in next lecture and will continue with the MCQs of semiconductors. Thank you for watching.